Okay, so a wire RST is connected to another wire XY as shown. Each wire is 100 centimeters or 1 meter long, with a resistance per unit length of 10 ohms per meter. So what is the total resistance between X and Y? So we know that the resistance of RST, because it is 1 meter long, then it is going to be 1 meters times 10 ohms per meter, and that will give us a resistance of 10 ohms. And then RT, which is only 50 centimeters, will be 0.5 meters times 10 ohms per meter, which will give us 5 ohms there. And then XRTY will be 1, because this whole XY is 1 meter long. So 1 meter minus 0.5 meters obviously equals 0.5 meters. And that will give you a resistance of 5 ohms. And so then now what we do is we think about it like it is a parallel resistor in series with another resistor. So this is going to be our parallel resistor. So we go 1 over 10 plus 1 over 5 equals 1 over resistance. And you put that into your calculator, and that should give you, and a quick tip on putting that in your calculator is you do, you go like this. And then that will just give you your answer, which is R, which is 3.3 ohms. And so 3.3 ohms is in series with this. So we do 3.3 plus 5 equals 8.3 ohms. And that gives you the total resistance. So the answer is C. A conductor consists of 3 wires connected in series. The wires are all made of the same metal, so we'll have the same resistivity, but have different cross-sectional areas. There is a current I in the conductor. Point Y is on the conductor is at 0 potential. So which graph best shows the variation of potential V with distance along the conductor? So we know that voltage is being used up as it goes through the conductor as it faces resistance, right? So it's just not realistic for us to have these stepped graphs. Another way to think about it is, so you know that resistance equals resistivity times length over area, and as it gets further away from X, the distance or the length increases, so the resistance increases, so it will get used up. So we just know that C and D are wrong. So now let's have a look at the last two. So we know that resistance is inversely proportional from the area. So the cross-sectional area. So the part of the conductor that is the thickest will have the least resistance. And we also know that resistance is directly proportional to voltage used up. So then that follows that the part that is the thickest, which has the least resistance, will have the lowest voltage drop. So we look at this is the thickest, so this should have the least voltage drop, and this has the smallest gradient, so A must be right. The graph shows how electric current I through a conducting liquid varies with the potential difference V across it. At which point on the graph does the liquid have the smallest resistance? So we know that resistance equals voltage over amps, and because we have I on the y-axis and V voltage on the x-axis instead of the other way around, we have to inverse this and think the liquid has the smallest resistance when the ratio of I over V is the largest. So if we draw it out from the origin like this, then we want to find the one with the biggest gradient, and the one with the biggest gradient is this one, so the answer is C. A common misconception that many people make is that, okay, so we've got this, so what if I just find the gradient across these points and I account for the fact that it is I, and like the axes are swapped around from what you normally have by inverting the reciprocal, because we've got this, right? But what you would really be finding with that is the change in voltage over the change in current. And resistance is not that. Resistance is just from 0. So what you do have to do is draw it back to the origin. So make sure you're not doing that. The resistance R of a resistor is to be determined. The current I in the resistor and the potential difference V across it are measured. The results with the uncertainties are current equals 2 plus or minus 0.2 amps, voltage equals 15 plus or minus 0.5 volts. The value of R is calculated to be 7.5 ohms, and we know how they got this because it is resistance equals voltage over current, and so they just did 15 divided by 2, and that gives us 7.5 ohms. And then they ask us, what is the uncertainty in this value for R? And so we know that to find the overall uncertainty, we are going to be using this, and we know that when we are multiplying or dividing, we simply just add together the percentage uncertainties. So percentage uncertainty of this one is 0.2 divided by 2, which will give us 10%. And the percentage uncertainty for this one is 0.5 divided by 15, which should give us 3.33%. And then we're just going to be adding them together, and that should give us 13.33%. And that's our percentage uncertainty. So to find the absolute uncertainty, we will times this number by 7.5 ohms, and that will give us plus or minus 1 ohm. Okay, so I've already drawn up the diagram, but this is a Wheatstone bridge. So it asks us, what is the current in the 40 ohm resistor of the circle below? So it does seem quite confusing, but I think that the Wheatstone bridges we will get in AS will be quite simple. So another way of drawing it is like this. And for now, let's just disregard this. And then we know that because the resistance are the same here and here, then it will have the same voltage difference across this middle 40 ohm resistor. And because there is no voltage difference, we know that I equals V over R, and if this is 0, then I will also be 0. So we know the answer is A. A power cable has length of 2,000 meters. The cable is made out of 12 parallel strands of copper wire, each with a diameter of 0.51 millimeters. What is the resistance of the cable? And then it gives us a resistivity of copper. So we know this and length, and this will also give us area, because we know that if we have pi times the diameter squared divided by 4, that will give us the area. And let's just consider one wire for now. So we also know this equation, which is resistance equals resistivity times length over area. And if we plug all our values into the equation, we should have 1.7 times 10 to the power 8 times 2,000 meters over pi times -3 squared 4. And that should give us, sorry, I was just busy putting that into my calculator, but what you should get from this is 166.4 ohms of resistance per strand of copper wire. And then we think about how they're 12 parallel strands, so you can think about it more as a parallel circuit with 12 resistors across it. So then we could think 1 over 166.4 plus 1 over 166.4, etc., equals RT. But since there's 12 of them, what we could do more easily is just do that times 12 equals 1 over resistance total. And so then resistance total will be this, inverse 1. And that should give us a resistance of the cable of 13.9 ohms, and we just round that up, and so we get C. For identical resistors, so let's say they all have a resistance of R, they are connected in the 3 networks below. Which arrangement has the highest total resistance and which has the lowest? So this one, let's say these two are in series, so this is 2R, this is R, this is R, and so then R total equals 1 over R plus 1 over 2R plus 1 over R. Put that in the inverse. And that should give us a resistance of 2R over 5. So number 2 is a little bit more complicated, but let's think about it as these two are in parallel, and then in series with this, and then in parallel with that. So we're going to figure out this first. So the resistance of this part equals 1 over R plus 1 over R inverse. And then to find it in series with that, we'll add R. And so that should give us 3R over 2. And then that is in parallel with this. So then we think, sorry, I don't really have any room. 1 over 3R over 2, or basically just this, plus 1 over R equals, that should equal 3R over 5, sorry, inverse. And so then that will give us the total resistance of that. And then for this one, then we have 3R here in parallel with this. So then it'll be 1 over 3R plus 1 over R inverse. And so then that will give us a resistance of 3R over 4. So looking at these, this is 0.4 R ohms. This one has a resistance of 0.6 R ohms. And this one has a resistance of 0.75 R ohms. And so then we know that this one is the biggest and this one is the smallest. So the answer must be C. The metal cube is measured by placing it between two parallel plates as shown. The cube has volume V and it is made out of material with resistivity ρ. The connections to the tube have negligible resistance, which expression gives the electrical resistance of the metal cube between X and Y. So we know that all sides of the cube will be equal length. So let's say this length is L. And so then we know volume equals L cubed. We also know that area equals L squared. And we also know that resistance equals resistivity over times length over area. And if we just substitute that in, we will get L squared. And so resistivity over length. And from this, we can switch it around. And so we can have length. We can have length equals cube root of V. And another way of writing this will be V to the power of 1/3. And so then we can have resistivity over V to the power of 1/3, which gives us the answer of C. So now let's actually run through the calculations. So this is in parallel, so we'll go 1 over 6 plus 1 over 6. And that will give us 3 ohms of resistance. And then that is in series with this, so we just add them together, which should give us 6 ohms of resistance. And then that is in parallel with this. So then we do 1 over 6 plus 1 over 6. And that will give us 3 ohms. Okay, and so then now we're going to have a look at this. And like before, we can just shortcut it because we know that it is 4 ohm resistors. So instead of writing out 1 over 4 in a row, we could just do 4 over 4 equals 1 ohm of resistance. And since this is in series with this, then we can just add together this, and that will give us 4 ohms of resistance. So that means the answer is B. Okay, and now we are on to the final question. So before we start this, we're going to say that resistance equals resistivity times length over area. Okay, let's go through this. A cylindrical wire 4 meters long, so the length, has a resistance of 31 ohms and is made out of a metal of resistivity of 1 times 10 to the negative 6 ohm meters. So what is the resistance of the cross-section of this wire? So let's put all the values that we have in. 31 equals times 10 to the power of -6 times 4 meters, and that gives us the area. So let's figure out what area is. Sorry, I'll just put that into my calculator. Okay, and so then if you put that into your calculator, you should get 1.29 times 10 to the -7. And then we also know that area equals pi r squared. And so then if we divide that by pi and then square root it, then you should get the radius of 0.000202, or 2.02 times 10 to the -4, which gives us D. If you have stuck around this long, thank you so much. We hope that you enjoyed this video. Please let us know what you would like to see next. And thank you for watching.